the second times root of t, which is just a
Just 1.
1. And of course, you can rewrite this as negative t e to the negative t, right? Root of 1 squared is,
1.
what's this squared?
Negative.
E to the negative t times e to the negative t. The negative times the negative is a positive, right?
It's e to negative t squared.
You get e to the negative t, and you multiply another e to the negative t.
There's a
Can't you add these exponents because you got the same base?
Yeah.
So you could think of it as e to the negative t parentheses squared, but we can add these. And what's negative t plus negative t?
Negative 2t.
I'm going to write it that way. Of course, you might be sitting there going, well, can't I just, I'm going to be hitting this on a calculator. Can I just do that? Yes, you can, but I want to write it one more time for you in case you're like, isn't that just e to the negative 2? And it is. Because you can, they have the same bases, you can add the exponents. All right, plus, what's this last one right here? Ooh, I'm just going to have to put a parentheses around this, right? Negative t e to the negative t plus e to the t, close the parentheses and put the squared there. You don't have to expand that right now because we're going to be hitting this on the calculator, right? Does anyone care that?
Isn't it e to the negative t variable?
Oh, you're the best. Right on. Thank you. He's like, don't forget that little negative t right there. And I'll write this again because we will be exploring this with our calculators. Negative t e to the negative t plus e to the negative t, and then we're going to square it. So now we can put this in a what? Integral. What's the limits? 1 to 3, and I'll put my dt, but calculator. That's what the TID 3 or 84. Was it Math 9? If you got an old one like mine, when I have to write an integrate, type it all in. If anybody needs assistance, put this in on a calculator. Go right ahead. This is what the TID 83 can do. Square root, your calculator, I'm going to put some parentheses. 1 plus e caret negative 2t. Plus parentheses, negative t times e caret negative t plus e to the caret negative t, and you got to square that, right? It's like all that squared.
We need a couple more parentheses, I think.
Right there at the end. I can make this one bigger so one can see this. That would close out this. Then I raise this to the what? All that squared, right? Then you write comma t, comma 1, comma 3. Using Math 9 off the TID3s, 84s. You don't have to use t, you can use it next, right? We just want to make sure everyone gets the same value. And if you don't get the same value, don't worry. Maybe after class we can just check with someone else's calculator. Maybe missing the parentheses like you're saying. You got to be very careful of it. Let me get it. What'd you get?
I got 2.045.
Anybody else get that? 2.045 is the length. Reach it up. Good job typing this in there. Being careful with all those parentheses. That's the older models. The newer models let you, with the math print mode, you know, get you actually put those, that's the integral symbol and everything. Pretty cool. That's like an old TID3 model. Can I erase? Right. Hey, one more of these. Then we'll do 13.4. We'll do motion in space. This is number 2. But again, because it's number 2 out of the textbook,
What the page number, Professor?
Yeah, this one I think you can do without the calculator. We'll see. We'll see what they got. They've got 2t, t squared, and 1/3 t cubed. You gotta go find the length of the curve. From t equals 0 to t equals 1. All right, what's r prime?
2t and t square.
Okay. What's the magnitude of r prime? 4.
4 plus 4t square plus t to the power 4.
So before I go jamming this in the calculator, would you all examine that? Can you simplify that?
Yeah, so
In
that's.
fact, I'll write it from the highest power to the lowest power. Let me factor that.
Yeah, that should be like t square plus 2 whole square.
I'll put that. T
Square
squared
plus
plus 2
2
times another t squared plus 2. So you get this,
whole square.
which I can simplify to what?
T square plus 2.
All right. Want to go with that? Cool. And if you want to put the bars here and go, okay, it would be the absolute value of that. But we're still going from 0 to 1. This is the first time we got a problem with no radical. No radical. Oh, what's that become?
1/3 t cubed plus 2t.
From 0 to 1. 1/3 plus 2 is. Yes, 7/3. Having a great job at that. We'll now do 13.4. And I just want to point out, hey, before we move on here, Aiden, I liked your question about like, why is this, the why part? Why is this happening? It's explained briefly on page 853, but they do reference section 10.2. That's what Art was mentioning, something from calculus 2, dealing with the actual arc length and curvature. So in this case, once you have that, this is what they had. I just want to point this out before I move on, because I like this question. And I'm referencing section 10.2 from the textbook. They got length is equal to this. F prime of t squared plus g prime of t dt. Okay, I got all the parentheses there, right? Cool. They just put a name tag, but it's stemming from that section that's allowing us now to, as you can see, like a connection there, is turn this into this vector r prime of t. This is just what? dx squared. What's that? dy dt squared. A to b. But now we can think of that as, oh yeah, this is the derivative of some x component, that's the derivative of some y component. that F and that G right there, and that's where we can actually think of this as coming about. But it does, I know it's short, and it's a little bit too quick there on page 853, but they are referencing section 10.2 on there. All right, when this is motion in space, let's derive this formula. So we're going to start with, oh gosh, just the gravitational pull. Sound good? So you and I are going to derive this. So don't ever think like, if you're worried about memorizing this actual motion in space, R of t, for any path today, you can always derive it yourself. It's not that bad. Let's just start with acceleration. This will be cool. This will be the derivation. How about, I'm going to put negative g, all right, just on the j component, right? There we go. Right, due to acceleration, there we go, we got negative g. Let's go to velocity. So we got to integrate, true? What's the integral of a negative g with respect to t?
No,
Oh, that'd be derivative, right?
no, that should
So
be,
that's like a negative 9.8, and I got to take its integral.
so negative gt.
I'll put negative gt on the j component, right? But isn't there a constant?
Yeah,
Okay, so I'm just going to put a plus c over here. Now, all we're trying to do is get the r of t. We're almost there. Almost there. We're at velocity. We only get the r of t. And this is in section 13.4. This is motion in space. And once we derive this, we'll work out a problem. All right, so in this constant here, I want you to think of this constant as the initial velocity vector. That's what it is. It's the initial velocity vector. So I'm going to put v of 0 for the constant. That's what the constant is. Now I'll go off to the side. Let you and I talk about this v at 0 right now. I'm just going to draw a picture. And we're thinking of initial velocity right here. The initial velocity vector. Can we think of its two components, x and y? What would the x component be? It'd be the magnitude of the initial velocity times cosine theta. And what would this component be? It'd be the magnitude of the,
y component.
yeah, the initial velocity vector times
Sine theta.
sine theta. So I'm going to write that here. Except now I'm going to write everything in terms of, I'll just switch from I was using standard basis form. I'm now going to write this in component form, okay? So what's the x component there of this velocity vector?
Initial velocity cosine theta.
And I'll even write it here before I change, substitute it in there. And when I'm saying this initial velocity vector has these two components. VO cosine theta and V naught sine theta. Now notice that this is going to be the first time, I'm just not going to put vectors on it. How about from here on out, let's just call this initial speed. We'll write V naught without a vector on it. That way it's a scalar. So that's what I have. You know, the magnitude of V naught would be the initial speed, right? So I'm just going to put a initial speed, cosine, sine, and now I'm going to rewrite this whole thing. All right, what's in this component? Yeah, V naught cosine theta. What's in this component? Don't forget about that. You'll have the V naught sine theta minus a gt. We got one more step to go. We'll have R of t. Did everyone see that? It was all based on this. This was the initial velocity vector. I'm calling this right here just the initial speed. I'm just not putting any symbols on top of it. That's the initial speed. So, one more step, we'll have it derived. What's R of t? This is the formula we use over and over and over again today. What's the integral of that respect to t? Cosine theta times a t, right? This throws people off, but aren't these all constants?
Yeah.
Yeah. That's like some at 62 degrees. That'll be like 55 meters per second, right? And we're just taking the integral with respect to what variable? t. That's the only variable we're integrating this with respect to. All right, what's the integral of that then? V naught sine theta
T.
t. Now what's the integral of a negative gt with respect to a t?
So minus G divided by 2 T squared.
T squared over 2. There it is. Hey, what about the constant? I mean, okay. Then you say what? Plus r of 0, right? There's your constant. So if you want, how about, because some things today may be thrown from a height, not everything's thrown from the ground, right? So we can just put plus an h naught in this component right here. That's what I'll do. I'm just going to add a little h naught right in there. But then when you just derive this thing, when I write it over here, I'll leave it up all class. I'm going to write the same exact thing, except I think here I'll put plus an h naught, because this thing may be thrown from what? Not everything's thrown from the ground. Some things are thrown from a cliff, from the top of a battleship, etc. So I'm going to write it here. R of t, V naught cosine theta t, V naught sine theta t, minus 1/2 gt squared plus, I'll put h naught in case it's thrown above the origin. Metric, we'll use 9.8 for G. US customary units, we'll just use 32 for G, right? Depending on the units they got. Good to go? Cool. Feel free to just start there, any problems. That's just two-dimensional, right? There's one problem, I'll make sure we're working today. I saw there's one problem in the textbook that they had it in x, y, and z components, and you're okay, then the z component can represent the height. Right? We can think of that as something being thrown, think of a pass being thrown off to the side or something. Okay, so here's the first problem we're going to deal with.